The universe is a vast mysterious place encompassing everything we've ever known, observed, or could ever hope to come into contact with. For millennia, a look up at the sky, our window into the cosmos beyond our world, was met with wonder, awe, and a fascination with the unknown. Thanks to all the scientific advances made by civilizations across the globe, we now know that the points of light in the sky are stars found grouped together in galaxies, which cluster together on the largest scales in a universe that began with our Big Bang a finite amount of time ago, 13.8 billion years. However, knowing that doesn't mean we know everything. In fact, the more we learn about the universe, the more we realize it is not what we expected. Throughout history, our understanding proved to be wrong, and surprises never seem to end. Accordingly, the experts are confronted over and over again with entities and processes that take known conclusions to absurdity. This includes an equally interesting and puzzling spectacle that scientists recently uncovered in an alien galaxy. What makes this new discovery so confusing, and what questions does it raise? All this and more will be discussed in today's episode of I200M. For as long as humans have roamed the Earth, we have sought to find our place in the cosmos. From the city-states of ancient Greece to the soaring capstones of the Egyptian pyramids, across the deserts and towering mountains of ancient China, down to the rolling plains of Mesoamerica, humans have sought to understand how the universe works. They developed mathematics to trace the motions of the planets, estimated the circumference of the Earth by walking from city to city, created star tables and timekeeping devices, and even recorded celestial events like Halley's Comet, supernovae, and eclipses. With time, we have refined our models of the universe using ellipses. Johannes Kepler reconfigured celestial motions. Galileo revolutionized Copernicus's heliocentric model of the solar system by discovering that the Sun, not the Earth, is the body around which all other elements of the solar system orbit. Isaac Newton developed the theory of gravity, which was later supplanted by Albert Einstein's theory of general relativity. Discovery by discovery, we paint in the gaps of the picture of our universe. And yet, somehow, with each brushstroke, that image morphs, evolving into something ever-changing, new, and unrecognizable. The universe that Kepler, Galileo, Copernicus, Kepler, Newton, Galileo, and even Einstein understood is different from the one we know today. Today's understanding of the universe is unsettling. It is not one that fits in a tidy little box with neat lines and a perfect lid. Our universe is mystifying, complex, and it defies expectations. For starters, our universe is not a static, enclosed entity. Our universe is expanding from everywhere, all at once. The fabric of space-time is stretching away from everywhere else, like an inflating balloon, carrying galaxies along with it. Photons traveling the lanes of the cosmos are stretched along with spacetime, their wavelengths growing ever longer or redder, thus redshifting with the expansion of space. Our universe isn't expanding into anything. To our knowledge, there is no extra dimension around the universe. Rather, space itself is expanding, causing the space between galaxy clusters, the largest gravitationally bound objects in the universe, to get bigger and bigger with time. And this leads us to the following unsettling conclusion: there's no center to our universe. Everywhere is the center because everything everywhere is moving away from everything else, all at once. But the universe isn't just expanding, it's accelerating with each passing moment. An unknown repulsive, persistent force, dubbed dark energy, is stretching the fabric of the universe. Dark energy is a fundamental property of space itself, invisible, smooth, and constant. And yet, we are entirely unsure what it truly is. And then there is dark matter, the invisible clumpy matter that binds galaxies together. In many ways, dark matter is the corollary to dark energy. Where dark energy stretches space apart, dark matter knits matter together. They are both invisible, neither interacts with radiation or light, and yet, they are ever present. Dark matter acts as the cosmic glue for large-scale structure formation, and dark energy is a principal ingredient in the universe's evolution. The afterglow of the Big Bang, known as the cosmic microwave background, is imprinted on the fabric of spacetime, a relic of radiation from when the universe was extraordinarily hot, dense, and smooth. By mapping its bumps and irregularities and comparing with galaxy surveys, scientists have found that 70% of the universe is made up of dark energy. Meanwhile, 25% is dark matter, and just 5% is ordinary matter. The remaining 95% of the universe is stuff that we can't see or don't yet understand. As such, despite everything we've learned about our universe, there are many existential questions that remain unanswered. We don't know if our universe is finite or infinite in extent. We only know that its physical size must be greater than the portion we can observe. We don't know whether our universe encompasses all that exists or whether it's only one of many universes making up a multiverse. And we remain ignorant about what happened in the earliest stages of all, in the first tiny fraction of a second of the hot Big Bang, as we lack the necessary evidence to draw a robust conclusion. But one thing we are certain about is that the universe has an edge, not in space, but in time, because the hot Big Bang occurred at a known finite time in the past, 13.8 billion years ago, with an uncertainty of less than 1%. There's an edge to how far away we can see. Even at the speed of light, the ultimate cosmic speed limit, there's a fundamental limit to how far back we can see. The farther away we look, the farther back in time we're able to see. And now, thanks to our best measurements of the part we can see, we're finally figuring out what lies beyond and how much of it we will someday be able to perceive and explore. But before delving into the unimagined objects in space, you first note that when astronomers talk about the universe, they almost always mean the observable universe. The word observable does not refer to the capability of technology to receive signals from distant galaxies or even if there is anything out there to be detected. Rather, it, as told, is a limit based on the speed of light itself. No signal can travel faster than the speed of light, meaning that there is a maximum distance since the start of the universe beyond which nothing could have been detected. There simply hasn't been enough time for light to reach us. This distance is called the particle horizon, which is analogous to the event horizon of a black hole. The universe can be assumed to be isotropic in all directions, which means that every location has its own observable universe when considered as the center or observer. When the world's most powerful space observation, the James Webb Space Telescope, focused its sharp infrared eyes on deep space, it detected a galaxy called JDS-GSC 13-0 found in the constellation Forks. JDS-GSC 130 is amongst the furthest known galaxies from Earth ever discovered and is at the edge of the observable universe. Due to the isotropic nature of space. If you were an inhabitant of this fairly small galaxy, the Earth would be at the edge of your observable universe. The light from JDS-GSC 13-0 was observed to be about 13.4 billion years old, less than 400 million years after the Big Bang when the universe was only 2% of its current age. In fact, the observation of this galaxy, so soon after the first stars were born, presented a challenge to certain theoretical models of galaxy formation. One might expect that this age would mean that JDS-GSC 130 would be 13.4 billion light-years away from Earth. However, the actual distance to the galaxy is 33.6 billion light-years. How can this be if the age of the universe is roughly 13.8 billion years? Surely there hasn't been enough time for light to cover such a distance. The difference between the so-called light travel distance and the actual distance is due to the expansion of spacetime. Imagine two dots on a deflated balloon, each representing a galaxy. If we inflate the balloon, we would observe the dots moving apart. The rubber of the balloon represents space, meaning the very medium in which the galaxies exist, expands. Edwin Hubble observed galaxies moving apart, and indeed, galaxies further away from Earth appear to be moving away from us faster than galaxies which are closer. Hubble used the analogy of raisins in a loaf of bread, which is more accurate than the balloon example as space expands in 3 dimensions rather than 2. Another important effect of the expansion of space is the effect on the wavelength of light. If we imagine a dash slowly traveling across the balloon between the two dots, it will get longer as the balloon expands. This is the same thing that happens to light as it travels, its wavelength increases. The increase in wavelength and a corresponding decrease in light's energy is known as redshifting. It is by measuring the redshift of light from distant galaxies that we can derive cosmological distances. All this means that, in the time it took for light to travel from JDS GSC 130 to Earth, the distance between the 2 points in space has greatly increased. In fact, the distance from Earth to the edge of the observable universe is really 46 billion light-years. The observable universe will continue to expand as time progresses, but interestingly, we will be able to see fewer and fewer objects. The universe is expanding faster than the speed of light, and so galaxies at the very edge, which we can see now, will, in time, become more and more redshifted until they disappear, and we will no longer be able to receive signals from them. It has been calculated that the maximum distance from Earth, which will provide a signal that will reach us given infinite time into the future and accounting for expansion, is 16 billion light-years. This distance is known as the reachable universe. In other words, we could still reach galaxies closer than 16 billion light-years if we left Earth today. The future visibility limit, the distance beyond which objects will never enter the observable universe at any point in the future, is 62 billion light-years. This is exactly equal to the current visibility limit plus the reachable limit, and this is no coincidence. The light that will ultimately reach us is right at that reachable limit to today. After journeying 46 billion light-years since the Big Bang, someday far in the future, it will arrive at our eyes. With each moment that passes, we come ever closer to our ultimate cosmic viewpoint as the light from the last galactic holdouts continues on its inevitable journey towards us in the expanding universe. A question to finish with: what is the true distance that light has traveled from JDS GSC 130? If the speed of light is fixed and the time in which it has traveled is also fixed, how far has it gone while the space is expanding? But this is not the only puzzle that JDS GSC 130 poses for scientists. A paper in April 2023 suggests that the most distant galaxy ever seen, taken by James Webb, isn't, in fact, a galaxy but a dark star with a mass of around 1 million times that of the Sun. Unlike ordinary stars, dark stars might not have been fueled by nuclear fusion but by the self-annihilation of dark matter, the invisible stuff that is thought to make up about 85% of the matter in the universe. The candidate star seen by James Webb will need more evidence to be confirmed. But if they're real, the finding could change our story of how the first stars formed. While waiting for scientists to solve these riddles, let's take a quick look at these new stunning images captured by James Webb. These unpredicted images caused a stir in the scientific community, unveiling that newborn galaxies look weirder than expected. For the longest time, many astrophysicists and cosmologists have assumed that newborn galaxies would look like the orbs and spidery disks familiar in the modern universe. But according to an analysis of new images from the James Webb Space Telescope, baby galaxies were neither eggs nor disks, they were bananas or pickles or cigars or surfboards, choose your own metaphor. That is the tentative conclusion of a team of astronomers who examined images of some 4,000 newborn galaxies observed by Webb at the dawn of time. This is both a surprising and unexpected result, though there were already hints of it with Hubble. Dheeraj Pandya, a postdoctoral fellow at Columbia University, is the lead author of a paper soon to be published in the Astrophysical Journal under the provocative title Galaxies Going Bananas. Dr. Pandya is scheduled to give a talk about his work on Wednesday at a meeting of the American Astronomical Society in New Orleans. If the result holds, astronomers say that it could profoundly alter their understanding of how galaxies emerge and grow. It could also offer insight into the mysterious nature of dark matter, an unknown and invisible form of matter that astronomers say makes up a major part of the universe and outweighs atomic matter 5 to 1. Dark matter engulfs galaxies and provides the gravitational nurseries in which new galaxies arise. According to Joel Primack, an astronomer at the University of California, Santa Cruz, and an author of the new paper, the result builds on hints from earlier observations from the Hubble telescope that the earliest galaxies were shaped like pickles. In an email, Alan Dressler of the Carnegie Observatories, who was not part of Dr. Pandya's work, characterized the result as important. It is important, extremely important if it is true. The study team analyzed the images of galaxies in a patch of sky smaller than a full moon, known as the extended Groth strip, which has been surveyed by many other telescopes, including the Hubble telescope. The images were obtained by an international collaboration called the Cosmic Evolution Early Release Science or SEER survey. The team plans to extend its observations to other well-studied areas of the cosmos. This will let us identify galaxies with different 3D shapes all over the sky and facilitate much-needed spectroscopic follow-up observations, Dr. Pandya wrote in an email. Galaxies are the city-states of the cosmos. Within the visible universe are an estimated 2 trillion of them, each containing as many as 1 trillion stars. But the visible universe is only a fraction of what's out there. Most of the matter in the cosmos seems to be in the form of dark matter,